Hi all together. Yes, my name is Dominik Töllner. As just has been said, I'm a PhD student at the Leibniz University of Hannover. And in this talk I will present you MELF, which is an approach to multivariant executables for a heterogeneous world. This work is a joint project with the Hamburg University of Technology. So let's dive into the motivation. Let's imagine we are software engineers in a company doing some database stuff. For example, we have this validate query function, which does some parsing and checks on the current client connection and the query that is actually executed. At one point in time, there's a customer saying, listen, something is wrong, my service is extremely slow, I need your help, please tell me what's going on. And you think, all right, what I can do is profile. I can enable profiling in my application, which allows me to get detailed data about function latency and builds a call graph. We can use gprof for this as an example, which injects mcount instructions and function calls to every function definition. You do that, and the client is all right with the slowdown. You gather your data, but then suddenly, at a later point in time, another customer joins this discussion, opens an issue, and says, listen, I don't know what you did, but whatever you did, please revert it. My stream is just so slow, I cannot access this service fast anymore, so please back off. And this is reasonable, because what you did is you activated profiling globally in your application, which means that this affects actually every customer in your system. So what you do is you revert. All right, you gathered some data, and now you need another approach to get this fine-grained information. Additionally, your boss comes to your side and says, listen, we need this profiling application. We want to make the customer happy. He pays a lot. He is important. But maybe we can fine-tune it a bit. Maybe we can make it customer-based. So what we actually want to have is some client-bound profiling to be able to only profile, for example, our customer A. The problem with the situations is that this first includes a lot of checks, so we have to pay for that a little bit. But also, we have to propagate this knowledge of profiling to our whole application space. It means our application has to be aware about this, that connections and clients can be profiled now, which can become extremely tedious, not only for your own code base, but also for linked libraries that you link against, for example. This is cumbersome, but there's a solution to it, which is called Multivariant ELF. And this is what I want to present you today. The approach of multivariant ELFs establish a multivariant binary format. That means that we do incorporate multiple compile-time variants of our program into the final executable. This is done on a function granularity and is coincidentally actually exactly what we need for our profiling setup to be able to only profile one customer of one function. In addition, we are providing an overlay manager, which is responsible to allow the concurrent use of these multiple variants across our application. It does that by a kernel extension for synchronized address spaces that we will explore in a little bit. We evaluated our setup in 4 case studies, naming a performance isolation, setup of profiling in memcached, dynamically selectable assertions, which we employed in SQLite, for example, connection-based or user-based, a context-specific application of address sanitization in MariaDB, where we are able to turn it on or off based on the current database user, and also a heterogeneous ISA extension setup, where we build a thread pool that is aware of this hardware. Due to lack of time, I just bring 2 with me today. The other ones can you explore in our paper. So let's build such a multivariant ELF. The first step in employing multivariant ELFs is, well, to generate the variants that we actually want to incorporate. So what we do is we take our source code and we just compile it twice. One time we include a compiler transformation of profiling PG, and the other time we omit this. We are left with 2 object files where one does the profiling and the other does not. Also, for both object files, we place our functions in their own sections. These sections are then used by the linker to build the final executable, and our work has been to extend the LLVM linker for the MELF approach to incorporate multiple variant output sections in the executable file. This is done in order to place each of the functions and their sections into dedicated variant sections in the output file to be able to place them at the same virtual address. This technique is called memory overlaying and allows us to exchange these sections during runtime to ensure that calls to these functions and function pointers, for example, remain valid after exchanging these sections. To be able to overlay these sections, they have to be of the same size so they perfectly fit, so we add some padding if needed. This doesn't happen on its own, so what we do need is an overlay manager to actually apply this exchange mechanism for our multivariant sections. We want to look a little bit deeper into the overlay manager for this talk now. As I said in the beginning, we are relying on the principle of synchronized address space views, a concept that I want to explain here a little bit. Traditionally, we are left with a process and a single address space, and address space views target to loosen this tight coupling between one process and its address space to allow multiple address spaces in the same process. Important to notice that these process address spaces are synchronized, which means that changes to their mapping, for example, if you call an mmap, are respected and employed to every single view, so they remain consistent and sound across all instances of this view. Also, most of their data is shared to allow for fast communication, but we're allowed to diverge at specific points in our memory map. And this is actually the property that we make use of here. For our MELF approach, we generate another address space. And the key idea here is to unshare our parts or our whole text segment to be able to exchange our variants, in this example, variant fast by a variant prof, which reside at the same virtual address that you saw before at OX2000. If we do that, function calls remain valid, and also function pointers, as you can see here, of foo in the heap on the right, point to the same function and remain sound and valid across all instances of all views. So what we are left with is a process with multiple address spaces where each thread can individually migrate between different views depending on their demand, if they want to execute, for example, the fast variant of our validate query function or the profiling one. So now what we did is we have been building MELFs. We incorporate multiple compile-time variants, and we allowed the exchange mechanism via our synchronized address space views. We also evaluated this in 4 case studies, and I want to present you the first one today, which is the performance isolation of profiling in memcached. The key idea here is to allow to bind our profiling state to certain connections, such as that we do have 16 worker threads on memcached that are connected to 16 client threads of memtier, a benchmarking suite for memcached. Each of these threads can spawn multiple connections, and we allow these connections to be either fast and performant or profiling. Over the course of the benchmark, we gradually increase the total amount of profiling connections to explore the penalty that we pay if one worker thread in memcached has continuously to switch between the profiling view and the performance view. So the key interest here is the question if we are able to describe the performance penalty of profiling and to shrink that impact only to the profiling connections and their threads, and to be able to keep the high performance of connections that are not profiling. What we see here is for the situation of 0% profiled connections, which means all connections are performance connections. We do not switch between implementations and views. We do pay a 0.11 increased higher mean latency for the request serving in our memcached. This is the base overhead for applying MELF. We do not switch, we do not make use of any variants, we are just using MELF compared to base memcached without any MELF. If we increase this to 75% profiled connections, for example, the performance connections pay an increased roughly 6% higher mean latency in their service latency. And this is due to the continuous switch between the profiling and the performance view that the worker threads in memcached have to actually execute to fill our benchmark. To put this into context, the 6% is still a lot better than its alternative. An alternative is to let MELF completely out of the way and just split everything with profiling, just as we do, where we do pay a 175% higher mean latency compared between the base memcached profiling is enabled and base memcached profiling is not enabled. As a second case study, I brought with me the heterogeneous ISA setup. So what we are left here with is our NUMA node core of 24 cores, where we virtually divide these 24 cores into two core groups. The upper core group, where we do not execute ISA extensions such as AVX2, and the lower group where we do execute code that makes use of these extensions to increase performance. AVX2 is enabled to enhance certain types of jobs. This is what you can see on the table on the top left corner, where we decided to create the two top jobs of Fibonacci calculations and matrix multiplications. As you can see, indicated by the snowflake running code with no AVX extensions, the Fibonacci and matrix multiplications are slower compared to, for example, the matrix multiplications on AVX2, which are able to gain the performance benefit. However, Fibonacci calculations on AVX2 enabled cores do not benefit from this because this is not suitable for this ISA extension. So the question here is, we're left with a heterogeneous ISA extension setup. What is the optimal way to dispatch our job queue of matrix multiplications and Fibonacci executions on our system? We built 3 thread pool abstractions for this, and the first one is a base pool where we do not use code of AVX2 at all. It's a very simple thread pool abstraction because we do not have to care about the ISA that we're actually running on. We use the base, it's slow, all right, but it's working. We just can execute, for example, Fibonacci and matrix multiplication on either core group, and it just works. Fairly easy at this level. The second configuration is a hard split. Now we do have 2 thread pools where we take care of that thread pools only issue and dispatch jobs matching the ISA that they are serving. So for the top group, we are only dispatching Fibonacci calculations, while on the bottom group, we are only dispatching matrix multiplication jobs because those are the ones actually benefiting from the AVX2 instructions. The third approach is what we have done with MELF. It's a combined approach. We do have a thread pool that is aware of this heterogeneous setup, and what we are now able to do is the thread pool can actually take care of running matrix multiplications on the AVX-enabled group, if possible, but is also able to dispatch and execute Fibonacci calculations to fully utilize the system. On the other side, also our upper group is able to execute the Fibonacci calculations as before, but also to run the matrix multiplications in case of our ISA group being fully saturated. So this is the core idea. Now we want to come to the results. What we do see here is our curve for the latency, end-to-end latency of 1,000 jobs of either Fibonacci or matrix multiplications, while slowly increasing the amount of matrix multiplications from the left to the right on the x-axis, while having the end-to-end latency on the y-axis. Important to note is that the end-to-end latency stays rather the same for about 60% of total matrix multiplications. After that, it starts to increase a little bit because these matrix multiplications execute a lot of memory. It has been like 565 times 565 calculations on the matrix, which is rather a lot. Our second pool configuration shows a strongly increased end-to-end latency, looking at the 0% matrix multiplication share, which is easily explainable by the fact that we have two distinct core groups, one that does run the matrix multiplications because they're faster, and one that does only run the Fibonacci. So what we are left here with is one single core group of 12 cores that are running Fibonacci, and the other ones are stalling. They're doing actually nothing. Obviously, as we're moving more to increasing the matrix multiplication share, it gets better to the point of 60%, and after that it starts to increase again. So what's the reason for that? If we take a look at the 100%, which is the highest point after the 60%, this is the same reason as before. Now we are just executing all 12 cores of matrix multiplications, but the Fibonacci stall. And the sweet point at the 60% is reasonable and understandable if we look at the table to the top left again, which is the ratio between the execution latency of the Fibonacci jobs and the matrix multiplication jobs. So those are the two pool abstractions. The final question is, where does MELF actually fit in this picture? And gladly, we do achieve the best end-to-end latency. And the reason for that is fairly simple. We are able to dispatch our matrix multiplication jobs on the AVX2-enabled core group, but we are also able to execute Fibonacci calculations on there if necessary, and the other way around for the other core group, which results in the effects that we are also lowering our end-to-end latency to the 60 up to 70% of matrix multiplication share. And after that, it starts to increase again. And the effect for this is the same effect as for the one pool based only, the red curve, where we are now running more matrix multiplications, and these are memory intense, and so they access a lot of data. So with this, I'd like to come to an end. What we've seen is MELF, an approach to the dynamic exchange of compile-time variants on a per-function level via memory overlay, while allowing a thread-level adaptation with our synchronized address space views. We've shown the applicability in 4 case studies. For example, the performance isolation, where we were able to, getting back to the motivation, isolate the performance penalty of profiling to customer A while leaving out customer B to a certain latency. We have seen the heterogeneous ISA-aware thread pool that is able to dispatch the workload according to the ISA of the job. And we do have the other 2 benchmarks, namely the selectable assertions dynamically and the context-specific address sanitizer, where we are able to utilize MELF to adapt to the database user that is accessing or the connection being made to SQLite, for example. With this, we are left with a variability mechanism for a heterogeneous word. And I would like to thank for your attention and gladly take your questions. Thanks.